Well, hello and welcome to the 14th lecture of this short course called Behavioral Theory of Systems with a view towards data-driven control. We were in the middle of proving, actually we didn't even start, we were in the middle of discussing the fundamental principle of algebraic analysis. What was that? Fundamental principle requires, fundamental principle answers the question to this particular issue. What is that? I am looking for solutions to this equation where this is a polynomial matrix, it's a polynomial differential operator in fact. It's a polynomial differential operator size G cross Q, and B is a given C infinity function. Yeah, X is unknown. X is an unknown C infinity function. Does X exist for a given B and of course the given differential operator? Fundamental principle says that such a solution exists if and only if for all R xi in R xi 1 cross G that satisfies such that R xi A xi polynomially evaluates to 0. We must also have R xi B action producing 0 trajectory. R xi annihilates the trajectory B. Then and only then do we have a solution, right? Let us try and appreciate this problem for some time. So, suppose we have this equation d dt plus 1 acting on x producing some b. What sort of b? Some function b. Do we have a solution for this? What will fundamental principle say? Fundamental principle says that indeed you have a solution. Why? Look at this guy as a polynomial. This is just xi plus 1. What is the value of g here? G is equal to 1, q is also equal to 1. So, it is just a scalar. This matrix is just a scalar. Now, what polynomial, what R xi takes it to 0? What is this R xi? What R xi can take this guy to 0? Remember, the polynomial, the set of polynomials, the polynomial ring is an integral domain where two non-zero polynomials can never multiply to give you 0. So, if this is 0, then that necessarily means that R xi must be the 0 polynomial. Only the 0 polynomial can kill xi plus 1. Now, if only the 0 polynomial can kill xi plus 1, then 0 acting on any old trajectory will produce 0. The 0 operator acting on any trajectory produces 0, isn't it? So, that means according to fundamental principle, such a solution X exists, there exists X, yeah, which satisfies this. For all B, for all C infinity B, we should be able to get a C infinity X such that this equation is satisfied. This is surprising, no? But it should not come to you as a surprise, because you know how do you solve for this? Well, you just use convolution integral, isn't it? This X will actually be given by 0 to t e to the power, this guy is e to the power minus t, right? This will just be, yeah, this is the input, yes, this is you just need e to the power minus t minus tau b tau d tau. That's it. That's the solution. One particular solution. There will be infinitely many other solutions if you add the homogeneous solutions to it, but at least one solution exists, which means all of C infinity, yeah, is actually contained in the image of the operator d dt plus 1. In fact, they are equal. It's kind of surprising, isn't it? Things will change drastically if you change this, this function space. If instead I want solutions in C infinity 0, yeah, or which is also denoted by D, yeah, is compactly supported functions. For compactly supported functions, I will not be able to write these things so easily. Indeed, when you are doing this convolution integral, even if B is compactly supported, this convolution integral, the result of that need not be compactly supported. Yeah. So, let us transform everything. I mean, let us shift all of this that we are doing to the compactly supported case. What happens there? So, to make our life easier, I look at this simpler equation d dt dx dt is equal to some b. Yeah, according to fundamental principle, as long as we are interested in C infinity functions, C infinity functions, not compactly supported, C infinity functions, we have, so for all b in C infinity, there exists an x in C infinity such that this happens. Yeah, how do you do this? Well, dx is equal to b dt. So 0 to x t is equal to 0 to t b tau d tau, right? Which then tells us that x t is equal to x0 plus b tau d tau, right? 0 to t. You can take x0 to be equal to 0. That's up to you, right? So this is the solution that I get. Okay. Now notice that, so C infinity, fine, fundamental principle works, but suppose I want compactly supported. I ask the same question for compactly supported trajectories. Does for all be compactly supported? There exists, is it true that there exists an x which is also compactly supported such that dx dt is equal to b? Is that so? Yeah, the answer is no. Indeed, why? Because what must xt satisfy? Xt is equal to xt x0 plus integral 0 to t b tau d tau, isn't it? Yeah, but then if that is so, suppose b is compactly supported. Let us see what is happening through this integral. Yeah, what is happening to this integral? Is the meaning of this integral. This is the t axis. Okay. Suppose b is compactly supported like this. This is b. Now what happens to this integral? Suppose this is t equal to yeah. So suppose this is some time t naught. Then at t naught, the value of the integration is this shaded region. Sorry, from 0 I have to integrate, right? From 0 I have to integrate. So the value of the function is this, isn't it? Yeah. At t1, the value of the integral will be this shaded region. At t2, which is at this boundary, it will be the value of this region, the area of this region. And then from beyond t2, wherever I go, it will still be this constant, no? So when you do this integral, the result of this integral will sort of keep on increasing and saturate at t2 and remain there. And this cannot be compactly supported. This is not compactly supported. So therefore, it's not true that for every compactly supported b there is a compactly supported x. So you see, the function space is important. Okay. So now here is the catch. Here is the question that for the C infinity case, why is it true that the fundamental principle works? What is so special about C infinity that this works? Yeah, things become more complicated when you allow these vectors, right? The general fundamental principle is for vectors, for multivariable case. This is the fundamental principle. And why is this true? It turns out that the answer comes through a mixture of what we have observed here with the scalar case, yeah, and an algebraic result, a classical algebraic result called the Smith canonical form. Actually, we don't need Smith canonical form in its full glory. Yeah, we can make do with a quasi Smith form, quasi Smith canonical form. Yeah, so through Smith canonical form and the observation that we have just made about the scalar systems, scalar equations, yeah, the fact that the solution exists because there is this convolution integral that you can evaluate to get a solution x. This is nothing but a particular solution x, which is guaranteed to be C infinity provided B is also C infinity. Yeah, so the mixture of this observation about scalar through convolution integral and the classical algebraic result Smith canonical form is what will give us the full result about the fundamental principle, right. So, first we understand Smith canonical form. What does Smith canonical form say? Smith canonical form in the easiest possible terms is as follows. Given a polynomial matrix G cross Q, yeah, there exists unimodular matrices U xi of size G cross G and V xi of size Q cross Q such that the following is true. R xi is equal to U xi D xi V xi. U is unimodular, V is unimodular, D has a very special structure. D xi looks like this. D1 xi, D2 xi, dot 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 up to dr xi. All these are zeros. This is an r by r square matrix. The remaining every entry is 0. So that overall this is the same size as R. This is G cross Q. Smith canonical form requires that D1 divides D2, D2 divides D3, so on dr minus 1 divides dr. But the quasi Smith canonical form, for that we don't require that. As long as it's diagonal, we are happy. This is Smith canonical form, right? Isn't it reminiscent of something? I'm sure you can see the similarities. This is very much similar to the singular value decomposition that you may have been aware of concerning real matrices, real complex matrices, constant matrices. But although they look similar, the similarity ends there itself. Yeah, the proof and everything is completely different, because here we are dealing with polynomials, there we are dealing with numbers. There U and V are not just singular and non-singular matrices, they are actually orthogonal matrices or unitary matrices. Yeah. But here they are unimodular matrices, things are polynomials, and proof techniques are completely different. But they look similar, and you can draw similar inferences as you can do with singular value decompositions, SVD, right? How do we prove this? I will just go through a sketch of the proof. Yeah, those who are interested can look at any commutative algebra books on one variable polynomial rings. Smith canonical form is a very popular result, so shouldn't be difficult for you to find out a proof. And the reference books that we are following, yeah, that will also contain the details, a detailed proof of this result. Okay, how do you prove this? Once again, the proof actually is an algorithm. So we have this R psi matrix. Okay, what we do is, for our first step, we do row and column permutation of rows and permutation of columns, so that the least degree element of R psi appears at this location. This has the least degree among all the entries of the matrix. You understand? You see, by row permutation and column permutation, you can take any element to any other point. Yeah, by doing finitely many row and column permutations, you can do this. In fact, just do, just take this guy here. If this is the least degree, just take this column here for first by column operation, and then take this row here by row operation. So by row column operations, you can bring this guy here. Now, row column operation means what? Permutation. Permutations are unimodular operations, right? Row operation will mean you multiply by unimodular matrix from the left, and column operation would mean you multiply by a permutation matrix on the right. Okay, a permutation matrix on the right. Correct. So you bring this guy to the least the least degree guy here, and then you do the following. Just like before, you divide with remainder through this column. These are these are row operations. This is an elementary unimodular row operation, and you can keep doing that together with row permutations, so that ultimately you have x and all zeros, right? This we don't know. This is how it will look like. This was the first few steps of the process that converts a matrix to an upper triangular matrix, right? Remember? Yeah, when you do this division by remainder, the remainders are of degree strictly less than the degree of this divider. So therefore, after each cycle, the degree is supposed to reduce. Yeah, so you can do this. Now, once you have done that, you do the column operation, right? So you multiply by V, this is V1, V2. So you do the column operation, once again, take this guy and divide with remainder. Okay, and you can bring this guys, you can, each time the degree will reduce. So the catch is that each time when you divide and then bring the least degree guy at this location, the degree of this location will reduce after each cycle. Okay, and this you can keep on doing as long as any of these entries. See, when you do this, when you are dividing through this structure may get hampered. Things will appear here itself. Yeah, but it doesn't matter. Each time you are doing, the degree is strictly reducing. Yeah, when you are doing this column operation, row operation, column operation, row operation, each time after the cycle, the degree of this guy will strictly reduce, and the degree is lower bounded by 0. It can never be less than 0. So after finitely many steps, it has to stop, and you'll have a structure which looks like 0 everywhere and 0 everywhere, and this guy is something. Yeah, and then it's the standard deal. You just forget about the first one, the first column, concentrate on this guy and do the same operation on this guy. Yeah, and each time this degree will keep on reducing. Yeah, so ultimately you know what will happen. This will become a diagonal matrix. Yeah, 0, and everything will become 0 everywhere. Unless they are all zeros, you will be able to run this process again, and so you will be able to reduce the degree further, but the degree cannot reduce forever, so it has to stop. Okay, I hope this is clear. Well, if not, you can look at the reference book, for example, and I will give you exercise problems which will give you more ideas as to how to carry out these operations. That will certainly clear up your ideas much more. Okay. So now this is my Smith form, Smith canonical form. I have given you only the proof of the quasi Smith canonical form, not the full Smith form, because full Smith form will require this divisibility, right? The second guy must be divisible by the first guy, the third must be divisible by second, so by transitivity it should be divisible by the first. So actually first will divide all of them, second will divide from third onwards all of them, third will divide from fourth onwards all of them. That extra property I have not included here, but that also can be included. Okay? Right. But now how does this help us in proving the fundamental principle? Well, here is the thing. Let's come back to fundamental proof of fundamental principle. So the first thing, what did we say? B belongs to the image of A xi if and only if for all R xi such that R xi A xi is equal to 0, we have R xi acting on B also is equal to 0. First, this direction, this is actually very simple. Since B is in the image of A xi, this implies there exists an x which is a C infinity function such that A xi x is equal to B. This implies R xi A xi x is equal to R xi acting on B, but this as a polynomial is the 0 operator. So 0 operator acts on a trajectory, must produce 0. So 0 is equal to R psi B, obviously. Yeah. So we have proven this direction. The other direction is the more difficult one. We need to prove the following. This is what we need to prove. Yeah. What does this mean? This means, so we assume, suppose for all R xi such that R xi A xi is equal to 0, we have R xi B is equal to 0. We want to show that there exists x in C infinity R Q such that A xi x is equal to B. That is what we want to show. Now, given this A xi, we obtain its Smith canonical form. So, we write A xi as U xi. By the way, there I did not finish this part. So, what if we did as the algorithm was that a series of unimodular matrices acting on R from the left, a series of unimodular matrices acting on the right. This product themselves must be is a finite product of elementary unimodular matrices. So, therefore, their product must also be a unimodular matrix that is equal to D, right. But because these are unimodular matrices, I have then R is equal to U inverse D V inverse. Okay. That is the Smith canonical form, trivial, right. So, A xi is of this form, A xi D xi V xi. Yeah, and the equation that we are trying to solve will then turn out to be U xi D xi V xi is equal to B, isn't it? Sorry, x is equal to B. What we do is we define this guy as y. But now notice, how are x and y related? V xi x is equal to y. I say x and y are uniquely related to each other. There is an isomorphism between x and y. Why? Because V xi is a unimodular matrix. You see, this means x is related with x is given by V inverse xi acting on y. So, the moment I have a solution for y, I have a solution for x and vice versa. So, therefore, I might as well concentrate on y itself. Now, so my equation becomes U xi D xi y is equal to b. Okay? Is that all right? Now, likewise, suppose there is an r xi which is such that r xi, u xi, d xi, v xi is equal to 0. What can I say about this product? Because this is a unimodular matrix, so if I define this thing as, let us say, S xi, then once again, just like the trajectories, I have a relationship between, so r xi and r xi u xi by definition is S xi. This means r xi is equal to S xi u inverse xi, right? So once again, there is a 1-to-1 correspondence between the two. For every S there is an R, for every R there is an S. Now, what can we say about this S guy? R xi A xi equal to 0 means S xi, this is if and only if, S xi d xi v xi is equal to 0. But v xi is a unimodular matrix, so this is true if and only if S xi d xi is equal to 0, right? But when is S xi d xi equal to 0? Look at this. What is the shape of d xi? D xi looks like d1 xi dot 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 up to some d. Should I use the same? It might be a little confusing for you. Let me use rho, d rho xi. 0, 0, and everything else is 0. This, yeah. What is it that kills this guy? If S xi multiplying d xi is equal to 0, then what can I say about S xi? S xi suppose is S1 xi, S2 xi, dot 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 up to S rho xi, then S rho plus 1 xi, dot 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 up to S, how many are there? G xi, right? This multiplies to d xi. What does it produce? This produces, of course, I will get rid of the xi's. This is just S1 d1, right? S2 d2 dot 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 S rho d rho, and then all zeros, right? Because these are just 0 rows. 0, 0, dot 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 0. How many of them? Q of them, right? Yes, Q of them. Q such entries are there. I think I have I've written it correctly. S1 times the D1. Yes, it's fine. Right, that's how it's going to look like. And this I want to be 0. Well, that means these products must be 0. But once again, these are integral domain. These are elements of an integral domain. So if they are 0, at least one of them must be 0. And I know that these D1s are non-zero. So therefore, S1 up to SR must be 0. So that means S must look like this. S xi must look like all zeros. How many of them? Row of them. And then S rho plus 1 xi up to SG xi, right? That's how it's going to look like. Now, such a thing kills. So, okay, R xi, U xi, D xi, V xi, X is what we have. And we also know that R xi, okay, this is equal to R xi B. We know that R xi B is equal to 0. What does that mean? Yeah, this means R xi, so S xi, U inverse xi, B must be equal to 0. Let us call this guy as B tilde. Yeah. So if S xi B tilde is equal to 0, that means 0 up to rho number of such zeros, then rho plus 1 xi dot 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 up to sg xi, that acting on b tilde 1 dot 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 up to b tilde how many of them, g, yeah, this is equal to 0, correct? But these guys are 0 and these guys are non-zero. If they are supposed to go to 0, then b tilde must have the form that up to b1 tilde, from b1 tilde up to b rho tilde, they are non-zero trajectories. These guys must be necessarily 0. Okay? That's what this means as far as S xi acting on b tilde being 0 is concerned. Okay. So then we have this situation. So R xi A xi equal to 0, implying R xi b equal to 0. This implies this thing implies, I mean, for all R xi such that this, we have this also. This means that we are dealing with this situation. We have u xi, we have d xi y is equal to b tilde, where b tilde has the form b1 tilde up to b rho tilde and 0, like this. The question is, does this mean we have a solution for y? Indeed. Why? Because it just individually, look at what this says. d1 xi must be equal to b1 tilde dot 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 d rho xi must be equal to b rho tilde, and we know that such individual scalar equations will have solution for all b1 up to b rho. Just take convolution integrals, yeah, corresponding to these guys. That's it. So we have a solution y. The moment we have a solution y, we have a solution x. Implies, just take x to be equal to, what was it, v inverse, right? Or was, yeah, x is v inverse xi y. Just take v inverse xi y and we have a solution x. That's what we wanted. This is what we wanted to show, right? So think about it. I think I had to rush a little bit at the end, but if you go through it one more time, I'm sure you'll be able to understand it. If required, go through these arguments more than once. We can have a small recap in the next lecture, yeah, where we will discuss the meaning of this elimination principle, meaning of this fundamental principle as far as elimination is concerned, and many more such things is what awaits us in the next few lectures. Till then, take care of yourselves. Bye.